Today, Mars stands as the very picture of an icy, hostile world. But it hasn't always been this way. Billions of years ago, rivers, lakes, and even vast oceans once rippled across our red neighbor's surface. Back then, Mars was seen as a promising candidate for life. So, what happened? What stripped away its thick atmosphere and drained its abundant water? Did Mars truly lose these resources forever? Surprisingly, maybe not. Recent findings from NASA's Mars InSight probe point to a groundbreaking possibility. Much of Mars' water may not have vanished at all, but instead lies hidden deep beneath its surface. If that's true, it raises a thrilling thought. Perhaps real Martian life could still be lying dormant within the planet's rocky crust. Stick around until the end to uncover the mystery of Mars' downfall, and why it might be far more alive than we ever imagined. Today, the planet wears the mask of death, an atmosphere so thin it can barely be called one, bone-chilling average temperatures of -60 degrees Celsius, and a parched, iron oxide-coated surface. It's no wonder modern science often calls Mars a dead world. If we rewind the clock by about 3.5 to 4 billion years, Mars reveals a completely different face. During what scientists call the Noachian period, our now desolate neighbor boasted a thick atmosphere, a powerful magnetic field, mild and stable temperatures, active volcanoes, and, most importantly, abundant water. And not just a few trickles here and there, but vast lakes, flowing rivers, and possibly entire oceans. In many ways, ancient Mars bore a striking resemblance to early Earth, where life was just beginning to take shape at the same time. But somewhere along the way, their stories diverged. So, what happened? How did Mars transform into the frigid desert we see today? And how can we be so sure it was once far more hospitable? The answer lies in decades of exploration. After Earth, Mars is the most studied planet in our solar system. Since the 1960s, countless spacecraft have visited the red planet, with 10 successful landings to date. Rovers and landers have been investigating its rocks, monitoring seismic activity, and analyzing its chemical makeup up close, offering us priceless insight into its past. And occasionally, Mars returns the favor by sending us its own samples to study. In particular, this refers to meteorites confirmed to have originated from Mars, offering valuable insights into the planet's mantle composition, signs of water-related weathering, and its past temperature and pressure conditions. But what ultimately caused Mars to die? Over time, our understanding of ancient Mars has grown increasingly detailed. For instance, just 2 years ago, China's Mars rover Zhurong uncovered new evidence suggesting that the planet once hosted an ocean. Findings indicate that, until about 3.5 billion years ago, Mars's northern lowlands were covered by a shallow sea, potentially spanning up to 20% of the planet's surface, an area comparable to the Atlantic Ocean on Earth. Today, however, no trace of this northern Martian ocean remains, and the same holds true for all other ancient water bodies on the red planet. Scientists widely agree that the disappearance of liquid water was closely tied to the loss of Mars's atmosphere. The primary suspect? The relentless solar wind, a constant stream of charged particles emitted by our sun. Over time, this powerful stream stripped away gas molecules from the Martian atmosphere, flinging them into space and leaving the planet cold, dry, and barren. The reason Earth hasn't met the same grim fate as Mars is largely thanks to our planet's magnetic field, which shields us from the solar wind's relentless particle theft. But this naturally raises a troubling question: could our own life-giving sun have been responsible for Mars's demise? To explore this, a research team led by Bruce Jakosky at the University of Colorado Boulder analyzed data from NASA's MAVEN probe and the Mars rover Curiosity. Their focus was on traces of the noble gas argon found in the thin remains of Mars's current atmosphere. This choice was no accident. Argon is an excellent marker for studying atmospheric loss because it doesn't bond chemically with rocks, meaning it remains as a clear record of escape into space. The scientists compared the levels of two argon isotopes. Over billions of years, the lighter isotope has been more likely to escape, leaving behind a higher proportion of the heavier one. By measuring this imbalance and assuming Mars once had an isotope ratio similar to Earth's, the team estimated how much argon the planet has lost. Their results were striking. Roughly 2/3 of Mars's original argon is gone. This pattern also revealed that much of the planet's carbon dioxide, a crucial greenhouse gas that likely played a key role in its once habitable climate, was also stripped away by the solar wind. And the magnetic field? Sadly, Mars hasn't had one for about 4 billion years. The culprit was simple but devastating. The planet's internal dynamo shut down, leaving its atmosphere exposed to the sun's relentless assault. A magnetic field forms when electrically conductive material moves within a planet's liquid core. On Earth, this motion is sustained by rotation, convection, and variations in temperature and composition. Together, these processes power the geodynamo, our planet's natural electric generator. Mars, however, is only about half the size of Earth, giving it a smaller volume compared to its surface area. As a result, it lost interior heat much faster, causing convection in its core to stop relatively early in its history. It's believed that Mars's magnetic field collapsed in less than 100 million years after the planet formed. Without this protective shield, the planet became vulnerable to intense solar radiation and the relentless solar wind. As a result, its atmosphere was stripped away, transforming what may have once been a life-supporting world into a desolate desert. Much of Mars's water was also lost to space, or so scientists thought until recently. Last year, researchers from the University of California, San Diego, made an astonishing discovery. By combining seismic data from NASA's InSight lander with advanced rock physics models, they found compelling evidence of something remarkable beneath the Martian surface. Their analysis revealed that the average Martian crust contains numerous cavities, making up over 15% of the rock's volume. Even more intriguing, these cracks, fissures, and pores appear to be filled with liquid water. According to the team, the most plausible explanation for their findings is that Mars's crust consists of fractured magmatic rock saturated with water. However, they note that this groundbreaking revelation still comes with one important caveat. It's possible that a massive water reservoir lies hidden deep beneath Mars' surface, but only if findings from the InSight lander's location apply to the entire planet. If they do, here's the exciting part: Mars could hold a vast reserve of groundwater stored in tiny pores within its deep rock layers, stretching across the whole world. Calculations suggest that the planet's middle crust alone might contain enough water to form a global ocean, covering Mars in 1 to 2 kilometers of water. In this scenario, Mars wouldn't have lost its water to space through atmospheric escape at all, it simply shifted underground. In other words, most of the water Mars once had likely seeped into its crust, where it still remains locked away as pore water. This hidden reservoir could also be one of the most promising places to search for life, past or present. Any potential Martian life would have evolved in an extreme, underground environment. Yet on Earth, we know of microbes that thrive in even the harshest conditions, so the possibility can't be ruled out. While the black smokers at the ocean's depths are sometimes suspected of having played a role in the very origin of life on Earth, the residents of the so-called deep biosphere are also remarkable survival experts. These hidden inhabitants, primarily bacteria, viruses, and fungi, flourish not only within ocean sediments, but also inside volcanic rock and even deep within the continental bedrock, kilometers beneath the surface. In line with the idea that, if it works here, it can work elsewhere, study co-author Michael Manga explains, since water is essential for life as we know it, I see no reason why Mars' underground reservoirs couldn't be life-friendly. Although we haven't yet found concrete evidence of life on Mars, we now know of at least one location that could, in principle, sustain it, and even provide a potential foothold for it.